My name is Alexey Shmakov. I am working in MicroSurvey team, and I will proceed to talk about MicroSurvey Solutions. Our team develops different custom features ordered by MicroSurvey software. In this presentation, I will give a brief overview custom objects that we have implemented, and I will tell you in more details one of them that has been created recently. At the previous ITC World Conference, my colleague Piotr Chekmarev presented the advanced Linetype custom objects. Let's briefly recap what it is. It is a big, complex entity. It allows you to create baselines that could be drawn with different complex 3D line types. Let's have a look at the example. Here are some baselines. There are arcs, a line, and spline. This is how baselines can be transformed to advanced 3D line types. Here you can see a water slide line type, a barrel line type, a chain link fence line type, and a divider line type. There are a pretty big set of different line types. To be more precisely, we have 100 different complex line types. Over the last year, we have made some improvement to this custom entity compared to the old versions. Now the object became fully 3D. In previous version, it could draw the line type in 3D, but the baseline segments must remain coplanar. Now there is no such constraint. Each segment can be located in different plane. Second improvement, drawing spline and helix segments also was added. The old version consists of line and arc segments, allows the user to draw more precise objects. In addition, we have improved drawing performance. Let's launch IntelliCAD, and we'll see a little example of this custom entity. Type align command. In the dialog that appears, we need to select line type you want. Note all kinds of line type are grouped by category to speed up search of particular line type. There are many different line types in every category. For example, roadway lines has such set of line types. Fence category such set of line types. We select, for example, W-beam guardrail line type, and we'll draw it. First, we are drawing a linear segments. After that, we are drawing arc segments. Further, we are drawing spline segments by feed points. And at the end, we are closing our entity. Switch to realistic mode. Here, what our objects looks like. That's all briefly about this custom entity. The next custom object that was implemented by our team is trajectory cone. The trajectory cone is used in MicroSurvey forensics application and is used to document the path of a bullet. It is based on the cone entity and has some useful features for users. On this slide, you can see a van that was shotted. Note the van looks sketchy because this is a 3D point cloud model that was scanned at the actual accident scene. At the vertex of the trajectory cones comes from the place where the bullet pissed car, and it extends along the axis of the corner to show possible bullet trajectory. The next custom object that was implemented is a drawing scale bar. The scale bar is just a measuring line with helpful features. And let's turn now to one more custom object that was recently implemented, the Body Poser 2D custom entity. What is Body Poser 2D? It is custom object that is used to position a 2D body in the diagram. The Body Poser allows the user to start with predefined pose, manipulate it further, and completely customize body pose. Let's have a look at this drawing. It is a schematic crime scene where the murder took place, and the user must draw a body on the diagram. The user may be a detective, police officer, or forensic scientist. These are not typical CAD users. It is important that this user can easily insert created custom objects in the diagram and manipulate it further with intelligent grips. It is the main purpose of this feature. We have implemented the following set of body poses: male front, male back, male right, male left, and etc. All of these poses have similar inner structures and behavior. How are they built? First, it is custom entity based on ODDB entity class. Second, a body consists of a set of separate parts. Each part is either a simple unit or a complex unit consisting of several simple child units. For example, a chest is a simple unit. An example of complex unit is a leg, as it consists of 3 simple child units: thigh, a shin, and a foot. Body posers are loaded from an XML configuration file, and each pose can be customized in real time. I will demonstrate it further. As I have mentioned, the body poser is described in the configuration file. You can see the simplified description of male body poser on the screen. The description of the body poser has following properties: name, body color, outline color, and many independent parts that make up the geometry of the body. Meanwhile, each part is described by such properties as position, name of the part, starting rotation angle, size, it is just boundary box of the part, pivot point offset, the part can be rotated 360 degrees from pivot point, so location of pivot point is managed by this parameter. Grip point offset, user rotate the part by selecting the needed grip points, so this parameter controls the position of grip points. And the last property, it is an appearance tag. It is responsible for how the part will be displayed in the body. An XML tag has a reference to a block entity located in a separate dwg file. This block is named as symbol. On this slide, you can see some symbols of a male back body poser. The block is drawn over the part. Every part is drawn independently, so we can shuffle a body part in the configuration file as we want. So, for example, we can easily build a male body part with a woman's chest. Now you will see how the user can customize the body poser in real time. Let's launch IntelliCAD. Let's open this drawing. It is a crime scene. There is a set of body posers on tool palette. Let's insert one of them. For example, I select female front body poser. Inserted objects looks like very big. Now we will customize it. How can I customize the body poser? First, a user can adjust the height and width with grips around the edge of the body poser. Change height width, change width, and uniform change. User can rotate the whole body on the plane of object. As I have already mentioned, every part can be rotated 360 degrees from the pivot point. For example, I rotate legs, shin, and only foot. We can do the same for arms. User can change body color from the property pane. For example, change color to yellow. User can change the outline color. For example, change color to green. User can select particular part and apply changes for only a selected part. For example, select some parts. And first change body color. For example, I will set blue color. I'm sorry, I select again. I set blue color. And second, user can set outline color. For example, I select magenta color. User can select body color by clicking on particular area of the body, or just user can select body part by name on the property pane. Head, chest, and further. Finally, user can select particular body parts and just delete it. Just delete them. Press delete button and selected body parts was deleted. Currently, the body poser feature has only 2D implementation. There is a plan for 3D implementation in the nearest future. All custom objects mentioned above have different internal data formats. The internal data formats may be modified from version to version as we add new features to the custom entity. For this reason, we need to support version control, so we don't break the old version in the new releases. So my colleague Piotr will tell you how we achieve this. Thank you for attention.
Hello, my name is Petr Chekmarov and I will speak today about custom entity versioning we are using in projects for MicroSurvey. Using custom entities is a natural way for describing complex subjects area. This description can be dramatically changed during development. Custom entities and their dwgDXF representation are inseparable. That's why users can have a lot of files with various formats of this representation, and we have to support all of them. I will tell you how we achieved this by the case of advanced Linetypes, our biggest project. Alexei Shmakov has already mentioned this, so I will not speak about its purpose and organization. I will better provide production statistics. There is 27 different classes to be stored in dwgDXF. Only 3 of them are ODDB objects, others are their members, members of members, members of members of members, etc. So we have a complicated structural hierarchy of objects where ODDB objects are entry points for the input-output functions. Before the first release, we started thinking about potential versioning problems, so we added the version counter equal to 0 at the start of all our ODDB objects. It's a standard recommendation from ODA documentation. We made dozens of changes in different classes between 2 releases, and before the second release we considered the problem seriously. Users might have files in earlier formats that we have to support. How can we read old version of classes? What is the principle of reading procedure, the writing of standard dwg in fields or its non-ODA equivalent? If the version is 0, it should be read one way. If it's different, it should be written another way. It becomes clear that the more versions we have, the more conditioned branches appear. What is more complicated is that the reading operation that has been basic before appears consisting of 3 important aspects: data extraction, its interpretation, and deployment. Interpretation is needed for each version except the last one. And the version n+1 comes, all interpretational conversions must be rewritten. The more versions there are, the more the semantic distance between read and deployed is. With such an approach, labor cost of creating a new version becomes linear, while the whole process of development is quadratic. At this point, Alexei Shmakov remembered that there exists a migration technique that interprets data before its extraction. Instead of converting all data to a new memory representation, it's simpler and more stable to convert file data between versions and extract and deploy data from the latest format. Then the labor cost of the new version is constant and development cost is linear. Let me remind you that input-output behavior of custom entity is defined through overriding the next set of virtual functions, providing the sequence of reading and writing of members object fields. There must be analogs of this function for non-ODA classes. You can see so-called fillers in the arguments. Basically, they are usual file streams. Having created our own version of file streams, we were able to write modified fragments of read files to our newly created streams. They can be deployed or processed one more time. We called the class that generates a new stream from the old one migration, and we called the sequence of all migrations inherent to the input-output objects migrator. Since migrations work only with streams, they can be described far separately from the class which dwg representation it works with. Let's review an example. You can see 2 versions of baseline class for advanced line types. Earlier we used string to store info about line types of classes, but later we found that it's better to use the enum for it. The essential strings here, code of migration, the essential strings here, wrstring and wrint32, are about taking out one field from the old stream and writing it directly to a new one without even an intermediate variable. Most part of migration code looks like this. Since modification most often affect 1 or 2 fields, migrations totally rewrite data read. So before any object is read, it is first processed by the migrators that actualizes the data if needed. Looks like we found the perfect solution. Yet no. The concept would be perfect if all objects were made of ints, strings, references or bools, but they also contain other complicated objects. Migration concept is a plain concept. It takes canvas of data on input and outputs another canvas without parsing it. For example, one of our class, fans, contains posts that can be described by profile or external block. Both are independent classes used in many places, not only for fans. That is the structure of external block. And this is a fragment of fans migration from 5 to 6 version responsible for moving the external block. You can see all the details of nested objects on a higher level of organization. It's long, it's monotonous, and we will see similar fragment almost in every fans migration, and it's just copying the piece of data from one stream to another. On the other hand, if object's member changes somehow between versions, migration will have to modify something in this data. By the way, migration of nested objects will do it itself, so it's possible and it's right to reuse this migration of nested objects in migration of container, like it's done for posts of fans for the same version range, but for profile described posts. Such code is shorter and, what is more important, it's centralized. This raises the question, why not read and write nested objects themselves within migration? Why not use their input-output functions, where it's obvious the sequence of reading and writing fields is naturally defined? In summary, because these functions are changed with versions, and using them in migrations would make the code much shorter but unstable. Now let's look at this diagrams and assume that migrations use input-output functions of nested objects. External block is a nested objects for fans. The header of the table stands for the version number. A dot in the cell means that there exists a corresponding version for these classes. Arrows designate migrations. Let's imagine that a file of 0 version is received. On reading, the migrator will be called. It will read all nested objects using their input-output functions that at their turn will call their own migrators that will back up the last version streams. Thus, after the first migration of the highest level, we will get the following picture. One of the nested members has the versions higher than the container does. So, is it bad? It's hard to say what can go wrong when the code written to support ancient stuff that you want to forget about will be dependent on a modern, frequently changing one. For example, fans migration from the first to the third version may need some field from the external block which has existed there before the second version and then disappeared. There appears consistency condition that has been met automatically in plain model. The whole stream canvas must move from the initial to the final versions evenly. That means that at each step of migration, the version of all nested objects must be lower or equal to the version of the container. But even if we had ability to somehow control on all levels the migration versions used, we still cannot use migration concept for version solutions that use input-output functions. This diagram demonstrated. On migration fans from 0 to 1, external block will be read with migration 0 free and can be written in the third version, but we must write it in the first or lesser version, in this case 0 version. We miss the writing operation in the 0 version. To pick this out, we need again to make semantic decay of operation and operation of migration this time. It decays to reading in the old version to appropriate data structure, init new structure of data with them, I call this transition relay, and writing it to a new stream. In the migration chain it looks like this. Now, when operations are defined, we just need to slightly rearrange them to get this scheme that will meet our requirements. That's how Ersatz appears. A carcass of object degenerated to input-output functions of a certain version and pure structural storage of all members corresponding to this version. Now let's return to the last diagram. With the help of zero version ersatz, we will read external block, and when fans asks, easily write it in the zero version. It's important that if some objects has never been modified, which means that it doesn't have ersatz at all, it may be considered as an ersatz of the zero version, an ersatz of the last version, and input-output functions of these objects will make the deal. Let's consider the details of the ersatz scheme implementation. All objects for input-output must inherit the MigratableOne class. To describe deployment, it asks fill the last version fields in memory. Functions with the internal suffix must be overridden. In code of this overridden for reading nested members, functions with full suffix must be used. They encapsulate all logics of migrations. You can see that the signatures contain version limitations. Read with what version, write with what version. It's needed to send the version deep into the tree of input-output functions. We can see the same signatures in the ersatz interface. And now there arises a question, how does reading to a certain version works? First, the dwgFullRead function of the object is called, and the dwgFullRead get core of ersatz. Stream are read by ersatz with closest lesser version to version of the stream. With the help of relay, we get the ersatz of the next version. Relay basically is responsible only for changes on the current structural level. Therefore, we have to synchronize a whole tree of objects to get a full value ersatz. So it must be written to a temporary stream, and a newly created ersatz must be read from it. Substantially, input-output operations forms the recursive bypass of the structured tree with the request to shift the version. Now this ersatz can be relayed again. Moving in this direction, we will initiate the ersatz of the target version, of the version closest to it, or the version closest to it from the bottom. There dwgFullRead stops and saves this ersatz. So if there appears a request to write it with a certain version, this ersatz will be migrated to the version needed and stored in stream. It's obvious that if a requested version of read will be higher than the version of last ersatz, the object will be honestly read, deployed with a dwg internal read, and after the write request will be also honestly written. A particular case is an object with no ersatz at all. Reusing its input-output functions, we can achieve usability we wished. However, we will start to transit the number of target versions deep into the tree, and we'll get the stream with the version we need. So much terms and concept. Is it really easy to use? Well, there is are three main rules in usual practice. Define input-output behavior through overriding dwg internal read, dwg internal write functions, even for the topmost object, also known as auto object. This is basically a naming convention. Second rule is object members inside are read written with dwgFullRead, dwgFullWrite functions. And third rule is the topmost object, auto object, must call its own dwgFullRead, dwgFullWrite function, asking for the last known version in standard orders input-output functions. It's an entry point for input-output issue. How to create a new version? Firstly, you modify on your needs your input-output functions, dwg internal read, dwg internal write. Second, you creating new ersatz and copy the containment of just changed functions there. Third, you write relay functions creating this ersatz from the previous one. And in the case when you first time modifying your object, you have to create zero version ersatz. Advantages of system we have created is that it's easy to use, it's stable. When you write in ersatz code, it's short and obvious. And one of the advantages is that versioning is strongly separated from the user code of class. you have no any references to the version in code of your class, you will always work with them like they have only one version. So that's all that I have. Do you have any questions? Thank you for your attention.